In this video, we're going to take another look at inverse trig functions. First, we'll look at solving equations with them and how their range restrictions can actually cause problems for us. Then we'll see what happens when you have a composition of trig functions and their inverses. These first three just ask us to evaluate the expression with the aid of a calculator. So I'll just make sure I'm in radian mode and then just get these three answers. And if I switch over to degree mode, I get these. Our calculator was treating arcsine as a function, so remember that on the unit circle, the range for arcsine is just the first and the fourth quadrants. So when we got negative 36 degrees as an answer, that makes sense, because there's some triangle in the fourth quadrant where the y value here, or the sine value, would be negative 0.6. But notice that the calculator did choose to answer this negative angle instead of going all the way to the fourth quadrant this way and giving us a positive answer. And that's because if you think back to the graph of arcsine, it looks like this, and it's restricted between negative pi over 2 and positive pi over 2. So if we had gone through that big positive angle, that would have ended up somewhere like up here on the graph. With arc cosine, the range is restricted to the first and the second quadrants, and our angle 75 degrees is right here in the first quadrant. Again, you can see that the triangle formed by this angle would have an x value or a cosine value of about 0.25. Now we know that there's another angle down here that would have the same cosine value, and this would be some negative angle. In fact, it would be negative 75.5 degrees. But our calculator is thinking of this as a function, and that helps it to know exactly which output it should give when we give it an input. And this last one was arctan. Remember that the range for arctan is just like arcsine. It's in the first and the fourth quadrants. And negative 71 degrees as an angle would be somewhere down here. It's going to be really helpful to start thinking of tangent as slope because we're going to deal with so many tangent values. So if you think of this tangent value, negative 3, as the slope, looking at this angle and thinking about if it has a slope of negative 3, that seems pretty reasonable there. So I'm just mentioning all this just to make some connections to things you've seen before, but also to point out that in each of these cases there were two places or two angles on the unit circle that would have given the same output value. But since the range is restricted according to these functions, remember because our calculator is using these as functions, it's only going to spit out one answer in the restricted range. Because when we move on to these questions, 4 and 5 say find two values of theta that satisfy the equation, and then I'm pretty sure this is just supposed to be a theta in here, so sine of theta equals negative 0.4. Give your answer in radians between 0 and 2 pi. So make sure your calculator is back in radian mode. And we're going to solve this equation. So sine of theta equals negative 0.4. So to solve this for theta, to get theta alone, we just have to get rid of sine, and we'll do that with its inverse function, arcsine. So this is kind of sloppy notation, but I'm just showing that we're taking the arcsine of both sides in the equation. And notice that you never see a trig function or its inverse written just by itself. Like you never see just sin. It always has some kind of input. And it's the same thing for arcsine. I'm writing arcsine here, but its input is the stuff in parentheses. So anyways, these two undo each other, and we're left with just theta on the left side. So if theta equals, and then on this side we would have arcsine of negative 0.4. And again, I'm writing my inverse trig function along with an input. And now this is not a special triangle type of value, so I'm going to have to use my calculator to evaluate this. So when you type that in, you get theta equals negative 0.4115. And it's just a coincidence that these decimal values happen to be so close to the input values. It was the same thing with this problem too. It's just a coincidence. So this is showing me that within the arcsine range, which remember that's first and fourth quadrant, there's one place on the unit circle. It's at this angle of negative 0.4115. I don't know exactly where that is because that's in radians, but I'm just going to estimate it's right about here because it needs to have a sine value or a y value of negative 0.4. But there's a few problems with this answer. For one thing, the direction said to find two values of theta, and so far we just have one. And for another thing, it said to find theta between 0 and 2 pi. And right now our answer is negative 0.4115, and that's less than 0. So it's not even in the correct range. Like the answer was in the range for arcsine, but not the range that the question was asking for. So we're going to have to play around with this answer for a little bit. For one thing, I'm going to label this angle negative 0.4115, but we have to think of this as a positive angle first. So to accomplish that, I'm just going to add one full revolution around the circle, and in radians, that's just 2 pi. So to get my first answer, I'm going to just type in negative 0.4115 plus 2 pi into my calculator and see what I get there. So it gave me 5.8717. For my second answer, I have to think visually on the unit circle, where's the other angle that would have the same sine value? So the sine value is negative 0.4, and remember that sine is like a y value, so I want another place on the unit circle that has a y value of negative 0.4, and that would be over here. So to think of what this angle is as a positive value between 0 and 2 pi, I'll start at 0 and go around the circle until I get over here. So in order to do that, I had to go through pi and then add a little bit more. So I'm going to think of this angle as pi plus, well, that little bit more was the same size acute angle as it was on the right. So it's basically this value, 0.4115. It's not negative though, because I'm just thinking of it as a reference angle. So pi plus 0.4115. And if you type that into a calculator, you get 2.7301. So here's my two answers for this problem. And now that we know the general process, this next problem will go a lot faster. So this problem is cosine of x equals negative 0.628. And to get rid of cosine, I'm going to do the inverse cosine function, which I'm actually going to use inverse notation this time, but it means the same thing it did up here. So we'd have x, or actually I'm just going to write theta instead, equals the inverse cosine of negative 0.628. So again, this is just calculator work because I have no idea what that value is on the unit circle. And my calculator gives me 2.2497, actually the 7 would round to an 8. So once again, we want to think of what that value means on the unit circle. So it's a radian angle, it's 2.2-ish, and I know that pi radians is over here and that would be 3.14. So it makes sense that this angle would be somewhere in the second quadrant. Also, we want to have a negative cosine value, so that means like a negative x value, and that's another clue that it would have to be over here in the second quadrant. So this x value would be the negative 0.628, and the angle we got was 2.24-ish, so I'm just going to write 2.2. Now the good news is that answer is in the range from 0 to 2 pi. In the first example, the calculator's answer wasn't even in the range to begin with, so we had to do extra work to get both of our answers. But in this problem, one of the answers given from the calculator is in the range that we want. So right away, I'm going to say theta 1 equals 2.2498. Now that answer was given because it's in the arc cosine range, and that's what the calculator is using. But I know that there's an angle down here that also has a cosine value of negative 0.628. So if you notice that up here, this angle, this obtuse angle was 2.2 radians. If you go in this direction, this obtuse angle would be negative 2.2 radians. But I can't answer that because that's not in the range from 0 to 2 pi. But if I use this as a starting point and then just rotate myself around the circle one full revolution, that means I'd have to add 2 pi to it. So this is like negative 2.2 plus 2 pi. That should be in the correct range from 0 to 2 pi. And if you type that into your calculator, it should give you an answer of 4.0334. And quick side note, you'll notice that with these radian angles, I usually go out to 4 decimal places because radians are kind of a big thing. Like 1 radian is about 57 degrees. That's a big portion of the circle. So to be precise, I like to include quite a few decimals in my radian answers. So back to the problem at hand, this answer we got, 4.0334, is in the correct range because 2 pi is about 6 point whatever, so this answer works. Now let's move on to taking compositions of trig functions and their inverses. In the past, when we saw compositions of functions, it just meant having a function inside another function, and that's exactly what this is. We have secant of arcsine of 4/5, and the second problem is cosecant of arctangent of 4/5. So you'll want to remember that the input for an inverse trig function, so this arcsine here, well, the input 4/5, that's a ratio of side lengths on a triangle. It's the same thing with arctangent. This 4/5 is a ratio of side lengths. And if I just looked at arcsine of 4/5, its output would be some angle, theta. So to start this problem, we're going to do it from the inside out. We're going to figure out what this looks like, arcsine of 4/5. That's going to be some angle, and then we're going to take the secant of that angle. And the hint says to make a sketch of a right triangle. So let's start there. So I have my right triangle, and I'm just going to label this angle theta. It doesn't really matter which one we pick. And since sine of this angle would be opposite over hypotenuse, I'm going to label this as 4/5 to match this ratio. So in this first step, in drawing this triangle, it doesn't really seem like we did any math, but it's kind of like we found this angle theta. I don't know the value of it because I didn't type this into my calculator, but I know it's this angle theta in this diagram. So for the second step here, I'm just going to consider what secant of theta would be. Well, I remember that secant is the reciprocal of cosine, and I know how to find cosine of theta. Cosine is just adjacent over hypotenuse, so I would have to figure out this adjacent side and then put it over the hypotenuse. And you might recognize that this is a Pythagorean triple setup. If you label this side 3, we would have 3, 4, 5. If you don't recognize the Pythagorean triples though, you can just figure out what the side is using the Pythagorean theorem. So the cosine value of that angle theta would be 3/5, but remember I'm looking for secant. So my final answer to this problem is just the reciprocal of that, which is 5/3. So let's do the same thing for number 7. The first step is to draw that right triangle and then label it accordingly. So we're looking at arctangent of 4/5. That's like saying that with this angle theta, the tangent value of it would be 4/5. And tangent is opposite over adjacent, So I'm going to label the triangle this way, putting 4 on the opposite side and 5 on adjacent. So here's my angle theta, and I have to now take the cosecant of it. Because we're saying that this arctangent of 4/5, we're saying that was equal to theta, or is equal to theta. So now we're saying let's take the cosecant of theta. So if you remember that cosecant is the reciprocal of sine, that means let's find the sine value of theta first. So sine of theta would be 4 over the hypotenuse. And this time it actually isn't a Pythagorean triple. Having 4 and 5 as the side lengths don't work out. Like I can't just label the hypotenuse 3 because then that would be shorter than this side length. So I will have to use the Pythagorean theorem and say 5 squared plus 4 squared equals, I'll just label the hypotenuse c for now and then say c squared. So this would be 25 plus 16, which would be 41. So the value of c is the square root of 41. So the sine of theta would be 4 over the square root of 41. And if I'm answering the problem as what the cosecant value is, then I just have to take the reciprocal of this. So it would be the square root of 41 over 4. These next two examples are going to be pretty similar, but now we have arctan of x over 8. So having one of the side lengths be x means we don't know the actual value of it. But that's okay because the directions say write an algebraic expression that is equivalent to this expression. So I'm not actually evaluating it, I'm just rewriting it as an algebraic expression. So let's do the same thing we did before, like I'm going to start by drawing a triangle, because this says that we have the arctangent of x over 8. So if I just label some angle theta here, because remember these are the side lengths, and its output of arctangent is going to be an angle theta. So from that angle, if I label the triangle so that tangent is x over 8, that would be opposite over adjacent, so I'm going to say this is x and this is 8. Now I have to take the sine of theta, and sine is opposite over hypotenuse. So I do need to figure out what this hypotenuse is, maybe not the value of it, but at least what it is as an algebraic expression. So just for now I'm going to call it c, and then I'm going to set up the Pythagorean theorem. That's basically step 2 of these problems. So I'll say 8 squared plus x squared equals c squared. And I'm just trying to figure out what c is, so the only step I need to do to solve this thing for c is just take the square root of both sides. So then I'd have c equals the square root of, and then you can simplify this a little bit, so we'll say 64 plus x squared. So the sine value would be x over that hypotenuse, the square root of 64 plus x squared. And I usually like to rationalize my denominators to get the radicals out of there, but since this is such a weird expression, it's not going to make it look much nicer to have it in the numerator, so I'm just going to leave my answer as x over the square root of 64 plus x squared. So let's do the same thing for number 9 now. It says arc sine of x minus 1. So I'm going to have to draw a triangle, label one of the angles theta, and it does have to be a right triangle. Now this is a little bit weird because x minus 1 isn't like a fraction, so if I'm thinking of theta as being opposite over hypotenuse, I would have to think of this as being like x minus 1 over 1. Like you can always change something into a fraction by putting it over 1. So arc sine of x minus 1 is basically this angle theta, whatever that actually is, but now I have to find secant of that angle theta. And secant is like cosine, so I have to know this adjacent side because cosine is adjacent over hypotenuse. So for now we could just label that side a for adjacent, and then set up the Pythagorean theorem again, so a squared plus, and then the other side is x minus 1. I'm going to have to put that in parentheses before squaring it, and that just equals 1 squared, which is just 1. Alright, so to solve this thing for a, the first thing I'll do is subtract this over to the other side. So a squared equals 1 minus, and then this stuff, x minus 1 in parentheses squared. And then to solve this for a, just take the square root of both sides. So a equals the square root of 1, and then I'm gonna FOIL this out. So it's minus all of this stuff, x squared minus 2x plus 1. And I just did that because then this 1 and this 1 will cancel out because I'm subtracting it. So then I'm just left with negative x squared plus 2x, because you do have to distribute this negative in here, so it changes the signs on those things. So we figured out that the adjacent side is this thing here, the square root here. But I'm actually going to rearrange that so it's the square root of 2x minus x squared, and then it just looks a little bit nicer. Alright, so I'm finding the secant. Remember, cosine is adjacent over hypotenuse, but secant would be the reciprocal, so hypotenuse over adjacent. So the answer to this question would be hypotenuse first, so 1 over, and then square root of 2x minus x squared. Again, since this is such a complicated expression in the denominator, I'm not going to worry about rationalizing it, because it wouldn't look much better with it on top. So I'll leave my final answer written this way. Now these next examples are similar. They're still technically compositions of functions because we have like sine of, arcsine of negative 0.2, or here we have arcsine of sine of pi. Notice that the order is changing, like the inverse trig function isn't always on the inside now. What's special about these 6 functions though is that the trig function and the inverse trig function always match up, so like sine and arcsine, or tangent and arctangent, or cosine and arccosine. So to some extent you can think of these as canceling each other out because they're inverse functions of each other. You have to be careful with that though, because arcsine and arccosine have restricted domains. Like they can only take inputs that are between 1 and -1. Whereas sine as a function can take anything in its domain. Remember, the sine graph went to the left and to the right forever, so it has all real numbers for its domain. So because the domains and the ranges of these functions don't always match up, sometimes we'll get an undefined result. And for that reason, I actually like to not just cancel these, but just treat them as compositions of functions and work them from the inside out. So if you type arcsine of -0.2 into your calculator and see what it gives you as a value, you'll get -0.2013, actually the 3 rounds to a 4. Again, it's just a coincidence that these values are so close to each other. But anyways, that's what arcsine of -0.2 is. So now if I want to take sine of that value, and notice that this is a radian angle because it's such a small value, that's a radian. So now I'm taking sine of -0.2 radians, and the answer I get out is -0.2. So in this case, it would have been okay to just cancel sine and arcsine and say that my answer is -0.2. That worked out. Let's see what happens with number 2. If we wanted to just cancel things and say arccosine of cosine of 7 pi over 2 is this answer, let's just see. So I'm just going to leave that on hold over here, 7 pi over 2. And then let's actually do this problem and see what happens. If I go from the inside out, I'm looking at cosine of 7 pi over 2. So 7 pi over 2, as an angle, that would be 1, 2, 3, 4, 5, 6, 7 pi over 2. That would be straight down here. And remember, with a quadrant angle like this, it's not a triangle, so I just take the point 0, -1. And remember that the cosine value is the x value. So cosine of 7 pi over 2 is 0. This whole thing is just 0 here. So now this is saying arccosine of 0. And that's saying find some angle where the cosine of that angle is 0. Like if you think of arccosine of 0 equaling some angle, you could say cosine of that angle equals 0. That's just the other way of writing this equation. But remember that the range for arccosine is restricted to just the first and the second quadrants. So 7 pi over 2 is actually down here. That's not in the first or second quadrant. So I have to find some angle up here that has a cosine value of 0 or an x value of 0. So if I don't want to go left or right, that means I want to go straight up, and this value is actually pi over 2. That angle is just pi over 2. And that's the answer to this question. So because it doesn't always work out where you can just cancel these out and say the answer is whatever you had on the input, that's why I like to just always do these problems from the inside out. Let's try the same thing for arcsine of sine of pi. So on the unit circle, pi is over here. It's another one of those quadrant angles. So this is the point -1, 0, and sine is the y value. So sine of pi is just 0, and now this is saying find arcsine of 0. Remember, with an inverse trig function, the input is the value, and the output would be some angle. So that's like saying find some angle, again, in the range of arcsine though. So that's just the first and the fourth quadrants. So I have to find some angle over here that has a sine value or a y value of 0. And that would just be straight to the right. And that's just the angle 0. So once again, I couldn't have just canceled out arcsine and sine and say that my answer is pi, because that's not in the range of arcsine. I had to answer 0 instead. This next one says cosine of arccosine of 2. Now if you remember this just kind of as a fact, that the inputs for arccosine have to be between -1 and 1, because I guess you could just think of the graph looking like this. So its domain, its x, or its inputs are between -1 and 1. You notice right away that this input of 2 doesn't work. So since the very first part of this problem is already undefined, we can't do the rest of the problem, because you can't take the cosine of undefined. But I guess if you don't remember that just as a fact, that the input 2 is outside of the domain of arccosine, you could just think of it this way. This is like saying find some angle on the unit circle that has a cosine value of 2. So an x value of 2. Well, having an x value of 2 would be way out here, and the unit circle has a maximum x value of just 1. So there's no triangle that has an x value of 2 and a hypotenuse of 1 on the unit circle. Like that, it just doesn't work. So for a couple different reasons, this problem is undefined. Number 5 says tangent of arctangent of 5. And at first glance, it might seem like this isn't possible because, again, 5 is bigger than 1. But now we have to remember that the arctangent graph actually looked like this. It went to the left and the right forever. So its domain is actually all real numbers, and 5 is totally fine. That's just going to be somewhere over here on the graph. So if we're drawing this on the unit circle to think about like arctangent of 5, that's like saying we have to find some angle theta where the tangent value is 5. And again, it's going to be helpful to think of tangent as slope. So let's draw an angle in the range of arctangent, so somewhere in the first or the fourth quadrant, that has a slope of 5. And that would just be some steep slope, so the angle would probably look like this. Now, we could label this triangle as having side lengths of 5 and 1, so that the tangent of this angle theta is 5 over 1, or 5. And it won't be on the unit circle anymore, but this angle theta will be in the same location. So arctangent of 5 is just whatever this angle of theta is here, but then the question is just asking to find the tangent of that angle. So tangent of this angle theta is just 5 over 1. So this is another case where we could have just canceled tangent and arctangent and said that our answer is just 5. But you have to be careful because that won't always be the case. In our last example, number 6, we have tangent of 3 pi over 2, which is over here. So with that being a quadrant angle, again, the point is 0, -1, but tangent is sine over cosine, or in other words, y over x. So that would be -1 over 0, and that's undefined. You can't divide by 0. So this would be like saying find arctangent of undefined. Again, that doesn't make any kind of sense. We can't do that. And another way of thinking of that is remembering that arctangent graph. Remember that goes to the left and the right forever, so there's no input value that is undefined. Everywhere in its domain is defined.